We are now on chapter 9, rotational dynamics. I will be defining torque, lever arm, and the definition of torque, basically the first section. The torque is positive when force produces a counterclockwise rotation about the axis. When the force produces a clockwise rotation, then the tau, which is the negative. So unit of tau is Newton meter. You can go to figure 9.2, page 219 to look at it. Okay, this is a better picture here. Look at this. How the force is acting, which way you turn the knob to open the door, or just trying to figure out the negative and positive tau. Now we are here. Tau is the magnitude of force and lever arm. So tau equals F times L. Go over example 1, page 219. Then we'll talk about rigid objects in equilibrium. The x component, sum of all x component has to be 0, sum of y component has to be 0, and sum of all taus has to be 0. You can go over example 3, page 221. These are the three conditions. If they satisfy, then only would say the rigid object is in equilibrium. The next topic, we talk about center of gravity. The center of gravity of a rigid body is the point at which it can be considered to have the torque due to the weight being calculated. Figure 1910, page 225, where we have W1, W2 at a distance x1, x2, and xcz is center of gravity. Then finally the equation becomes xcz. We are interested to find the center of gravity. So W1 x1 plus W2 x2, so on and so forth, depending on how many weights you take into account, divided by weight, W1, W2, all total. This is another interesting picture, which is a little bit enlarged. I couldn't fix it out. So you can go into your textbook and figure out this one. Here is the center of gravity picture. You have W1, W2, x1, x2. Then we are interested to find out where the center of gravity is working. So that is xcg. And the equation we'll be using is this, which is W1 x1 W2 x2 divided by W1 plus W2. We'll see how the Newton's second law is applied to rotational motion about a fixed axis. We'll consider the tangential force, which is Ft I told you that in previous chapter. Then you have force equals mass times acceleration due to tension or tensile acceleration. Finally, tau equals ft times r, or tau equals m a t r. And finally, the equation becomes tau equals m r square in parentheses times lambda. So we consider here lambda as the acceleration. So we have finally a new term here, the moment of inertia, which is tau equals I times alpha. Sum of all the external torque equals, in parentheses, sum of m r square times alpha, which is moment of inertia. So the external forces equals moment of inertia plus angular acceleration. Then finally, this is the equation you have, and you can compare that to force equals mass times acceleration as per the Newton's law. There is one table which is 9.1, and that will be helpful to solve problem. You have different objects with moment of inertia shown to you. Okay. Now rotational work and energy. Work equals tau times theta. Theta is always measured in radians. Then ultimately you will have kinetic energy equals half times sum of mr square times omega square, which is similar to Ke is half mv square. And kinetic rotational here is we take into account moment of inertia, as you see. So that is half moment of inertia times omega square. This all measurement of work and energy is in joules. Remember that, please. Now the last topic we have here is 9.6, which is angular momentum, L, I times omega. Omega has to be measured in radians per second. Here unit is kilograms times meter square over second. The total angular momentum of a system remains constant or unchanged if the net average external torque is acting on the system is 0. So you can go over figure example 13 in 239. Refer to figure 913 on this page, which is 239. However, you can always see what happens to aircraft being taken up with a normal force. This is pretty much in this figure here. This is another picture showing you in figure 916, which is not a regular shape of the object, it's a different type of shape. And here the last picture I have to show you is this. This skater is moving the one leg, as you see the circle in the central axis here, and this is rotational motion. Here the conservation of tau takes place, which you can figure out looking at the picture here, and you should also go over example for angular momentum. Please go over this reference, which is 913 page 239. This is a very good example for angular momentum. That's all I will say for tonight, and there will be announcement for the next exam, which will be in couple of days. I'll let you know, guys. Okay, thank you so much. Have a good night.